I'd like to make three initial points. That I'm talking here about tools which respect three important things about the real world. The first important thing is that the real world is dynamic. What that means is it's subject to small parts, each of which have a different rate of change. If I was to express that mathematically, I'd say the problem is governed by the solution of partial differential equations, because each little part is changing at a different rate and they're all interacting. So it's a fundamentally dynamic system. So what I'm saying here is I'm not concerned with models that make simplifications or assume steady state conditions or whatever. We must respect the dynamics. The second thing is the energy systems we're talking about here are nonlinear. What that means is the parameters which define the problem is a function of the state variables which tell us about its performance. The conductivity of the brick is a function of the temperature of the brick. We can't get the temperature of the brick without having the conductivity of the brick. Classic nonlinear problem. And we must respect that too. So I'm talking not about systems where you put in fixed time invariant parameter definitions, like a U value, for example. That would have no place in these models because it doesn't mean anything in this real world. And they're also systemic, which basically just means that there's all sorts of parts interacting one with the other. So when we try to capture daylight and we're opening and closing blinds and sympathetically switching off and on electric lighting in order to have daylight utilization to save electrical power, we're also interacting with another system that's perhaps a PV facade that's trying to get the same access to the sky in order to generate power. So unless we respect those systemic aspects, the link between comfort and energy and lighting and lighting and comfort, then we're not really addressing the real system, and therefore we're not considering it here. The approach I'm talking about, if we can achieve it, defines best practice, because we're now respecting all the time-varying temporal aspects. We're integrating all the technical domains, the air movement, the radiation fields, the conduction, the convection, the advection, the technical systems and control, and the heating and ventilating and cooling plant, the renewable systems. They're being integrated. The moisture flow is integrated. It supports cooperative working because different specialists enter into the cooperative process to bring their specialist knowledge to evolve the description of the real world, which gives you the performance benefit. It enables realistic life cycle assessments because you're looking at the whole picture over as many years as you want. It links building design to wider issues because we now can see how we relate to all the other policy or economic or social aspects. And frankly, it's cheaper, quicker, and better than anything that's gone before, as long as it's well captured. Let me give you just three examples of such tools. And I'm going to borrow these examples from the work of my own group, but I'm putting them across to you today as generic examples where you will find a range of instances of different programs in this class. So the first system is, we have system NTRAC. It's energy management and action planning. And basically what it does is it gathers together information on actual energy use in estates. And those estates could be the estate of Glasgow City Council, the estate of the University of Strathclyde, the estate of some nation, housing stock. So it gathers the meter data. So therefore that is a dynamic model because it's got the actual use of energy from the different use streams. So it makes a database. Into that database, we can apply interrogations. And those interrogations can be anything that we conceivably are interested in. And I'll give you an example in the next two slides. And those interrogation results can then be layered over some suitable way of delivering the information. Here shown a GIS map of a part of the city of Glasgow to the north, Springburn. So that those who are interested in looking at dynamic trends of demand, energy demand, different authorities right down to citizens who might be wanting to see what's happening in their street or in their individual property, can then make decisions based on actual information and consumption and emissions and profiling of properties and looking for areas of opportunity. Uniquely, in such a system, if it's well tailored, scenario simulations can be conducted by anyone, and they can use appropriate tools. And I'm going to show you two appropriate tools in a moment, one called Merit, one called ESPR. And tools like these, and there's many examples in the world of this class of tool, tools like these can be used to do scenario investigations of future change at different levels of detail. And that information can then coexist in the core database. So now we can be mixing the now and the future in order to support rational change, dynamically, non-linearly, and systemically. Here's one example of the application of such a system, where you may have interrogations relating to show me the energy use at the moment, show me in coloured pictures heat to power ratios, because I'm looking for a cluster which presents a constant heat to power ratio where I can deploy my biomass CHP plant. Because if the heat to power ratio is varying too much, I can't deploy it. Tell me a little bit about daylight access or solar access. So the analysis would be not only in terms of where the building is, but something to do with its height, and its height in relation to the height of surrounding buildings and obstructions. So we can rate solar access or sky access. Fuel poverty. It might be that somehow you put economic data onto it. So you're limited only by your imagination. Here's another application of the same system, where here the information coming back was the prediction of the yield of a wind farm when placed in different possible places at the north of Scotland, tip, Caithness. So these would be the subject, some years ago, of a planning application for a wind farm development. And the developer had ran the numbers, saw the yield, and into NTRAC it goes. What NTRAC does is to look at the proposal from a technical and a policy point of view. This is the technical point of view. This is, do we have good transmission or distribution network access? Can we get to the site? Do we have road access? Is there a good wind resource there? Is it windy? On the other side, we can put non-technical policy aspects. Is it too near to a dwelling? Is it in a microwave link corridor, communications corridor? Is it on a site of special scientific interest or scenic beauty? And these can be rated so that green is saying it's a perfectly possible, and green here it's saying it's a most favourable technical. And what we found when we did that was that any site that was technically feasible was policy constrained. And so we had a system in the UK whereby the developers would go to the planners who would turn them down after about a year's effort had gone in. Whereas if both sides could simply sit down with a system like this, they could look for areas of mutual opportunity. Now, there's commercial interests and other issues to be taken into account, but at least it's rational. And it's dynamic, non-linear, systemic, because it's joining everything up and it's looking at real trends. The second example is a system called Merit, and that's about matching supply and demand. And what it does is to allow you to arbitrarily define a demand. So that might be the demand for electricity for the City of Glasgow, or the demand for electricity for this university, Glasgow Caledonian University. And of course you can have demand 2, demand 3, demand 4. So demand 1 might be the energy demand for Glasgow Caledonian University, and demand 2 might be a projected demand after some refurbishment. Just whatever you want. And that could have come from NTRAC, monitored, or indeed it could come from the next tool I'm going to show you, simulated. So you'll have as many demands as you want, one shown here, and then you identify all the supply potentials that you believe are feasible. Arbitrarily, and you identify them all. You're not suggesting here they're all going to be used together. You simply just identify, I'm interested in PV, I'm interested in biomass, I'm interested in big PV, small PV, moderate size PV, big CHP, small CHP. You know, you could put 25 supplies in, all CHP, 1 kilowatt, 5 kilowatt, 10 kilowatt, you know, because you just want to see what works. And all Merit does is a combinatorial matching process. It just says, can I match demand 1 with supply 1? Can I match demand 1 with supply 2, with supply 3, and so on? Is it better if I use supply 1 and 2, or supply 1, 2, and 3, or supply 1 and 3, or supply 2 and 4? Combinatorial, it searches. And then at the end of it, it will let you look at the best one, the second best one, the third best one, right down the list of results in terms of how much, what the match will be like, what's the residuals and the deficits, what the auxiliary would need to be if you had storage or whatever.